Okay, it's been a while. Um, Hopefully, I'm not out of shape for doing these, but we'll give it a shot. Okay, so you should have seen a video on what harmonic motion is, simple harmonic motion. And there's really two types of simple harmonic motion. There's a weighted spring, and then there's like pendulumic, a pendulum swinging back and forth. And if you watch that video, that's what that guy that was holding the apple moving back and forth. Harmonic motion is one application, or simple harmonic motion is one application of how we use sine and cosine waves. Okay, so the way that a simple harmonic motion function is defined is in terms of d, because d stands for displacement. Um, Not necessarily movement, but if you consider straight up and down as being what we call equilibrium, right? At rest, an object will swing in one direction to its maximum displacement, pass through equilibrium, and then swing to its another part of its maximum displacement, right? So the displacement from equilibrium is the same in this direction as it is in this direction. Okay, so that's why we're measuring displacement over time. This is what a basic simple harmonic motion function looks like for a sine wave. A is still the amplitude, okay? But we call A maximum displacement when we're in this context. And I've used that term before in class, so that should not be anything new. T is still time. That's our independent variable. What you'll notice is not missing here is you're not, what's not missing? What's not here is a vertical shift, and we're also not talking about a phase shift. So both of these variables are inside that sine function. This W looking shape is not actually W, it's a lowercase omega. Okay, capital omega looks like that. Lowercase omega looks, it's really, there's like a loop-de-loop in there, but that's immaterial. But all that means is that when we're talking about the period of this motion, of the wave that describes the motion, instead of finding that by doing 2 pi over b, we're doing 2 pi over omega. Okay. And then the same thing can be said for cosine. So a couple of terms that are going to come up here, and I would encourage you to pause this to write these down in your notes, are oscillations and frequency. Okay, these are kind of physics-based terms. So an oscillation is a unit that measures the complete physical cycle of an object in periodic motion. So, for example, if you think about that swing problem that we did with the eyeball on the swing, uh, equilibrium of the swing would be right here. Okay. Now, one period of that motion, I mean, obviously a swing doesn't go from straight up and down to moving, right? I mean, you usually like pull yourself back, right? When you're on a swing, and then let yourself go forward and then back again, right? So if you consider what one oscillation is, it would be going from maximum displacement here, swinging all the way out to maximum displacement here, and then swinging all the way back. So the oscillation, if I could trace this again, is from here and then back. Now, if something starts at equilibrium, which is possible, and then goes up to a maximum, back to its minimum, and then back, that's one oscillation, right? And we'll talk about that when we look at some of these examples. Frequency is the number of oscillations per unit of time. So frequency is actually related to period, and we'll talk about that when we see one of these examples. It's actually, though, the reciprocal, okay, of the period calculation in terms of frequency. Because if you think about it, well, we'll get into it. I'm going to leave that I'm going to leave these 2 points just like this. Make sure you write these down in your notes, and then I'm going to start again with another video here in a second.